Buon pomeriggio a tutti e a tutte. Oggi per noi è un grande giorno, è l'evento di chiusura di Webvalley. Ogni anno per me è una grandissima emozione arrivare qui e arrivare a questo traguardo. E quest'anno la tematica scientifica proposta ai nostri ragazzi è stata, io posso dire, davvero sfidante, e la squadra dei tutor, ce ne sono parecchi qui presenti oggi in sala, e i ricercatori coinvolti è stata davvero di altissimo valore scientifico. Abbiamo lavorato con 20 studentesse, studenti provenienti da diversi paesi, culture diverse. Avete collaborato tra di voi, avete lavorato duramente, direi, e siamo arrivati e siete arrivati a dei risultati che tra poco ci presenteranno. Abbiamo avuto l'onore, direi, di lavorare con i colleghi delle unità della Fondazione Bruno Kessler, di Data Science for Health, di Data Science for Industry and Physics, con il Dipartimento di Fisica dell'Università di Trento e l'Istituto Nazionale di Fisica Nucleare. Mi fa piacere ringraziare un collega che appunto mi scuso se abbiamo aspettato un po', ma magari poi lo salutiamo di nuovo alla fine, però è il professor Juppa, per cui grazie anche a lui la Webvalley di quest'anno è stata possibile. Glielo racconterete, ma lo vedrà anche nella registrazione. L'aneddoto è che noi a settembre abbiamo fatto un pranzo con Giuseppe e con Marco Cristoforetti, gli abbiamo raccontato di Webvalley e abbiamo provato a coinvolgerlo e gli abbiamo fatto la proposta di questa Webvalley, direi spaziale, se mi posso permettere. Lui ha accolto l'idea e ha messo a disposizione una squadra di ragazzi davvero fantastici, quindi grazie mille. Io do poi il benvenuto al comitato scientifico, che vi ringrazio, avete accettato di partecipare a questo momento di chiusura della scuola e vi coinvolgeremo nella discussione, nei commenti, diciamo, di chiusura, quindi vi lasciamo lì comodi perché così riuscite anche ad apprezzare il lavoro fatto dai ragazzi e dalle ragazze. E sono Leonardo Ricci, professore associato dell'Università di Trento, Francesco Nozzoli, ricercatore senior di TIFPA e di ENFN, e Francesco Domiccoli, postdoc dell'Università di Trento, quindi grazie mille. L'anno scorso vi abbiamo anticipato proprio in questa sala che stavamo collaborando con gli Stati Uniti, con la South Florida University, per estendere il modello di Webvalley anche negli Stati Uniti. La collaborazione è andata avanti. Quest'anno abbiamo avuto 2 studenti dal South Florida che hanno partecipato a Webvalley e abbiamo anche 2 professori, a cui magari alla fine chiederemo anche un saluto, che sono stati con noi questa settimana come osservatori, hanno accompagnato gli ultimi giorni di questa Webvalley. Non vi rubo troppo, ma mi piace ricordare e ringraziare la collaborazione con i colleghi dell'Istituto Artigianelli. La scuola ospita ormai da diversi anni i laboratori di Webvalley, contribuisce in tutte e 3 le settimane mettendo a disposizione il suo personale docente e che ci accompagna anche proprio negli aspetti di, diciamo, didattica innovativa, costruzione del team di lavoro. Un grazie al Collegio Arcivescovile che ospita i nostri ragazzi e all'Art Café che grazie insomma alle sue ragazze Virginia, Arianna e Agata quest'anno ci hanno preparato colazioni, pranzo e cene tutti i giorni. E adesso io passo la parola a Giuseppe Jurman, che ormai è dal 2009 che siamo affiancati in questa avventura, coordiniamo la scuola da diversi anni e ogni anno per noi è una conferma del valore di questa esperienza per tutti noi e anche per i ragazzi. Quindi io passo la parola a te, approfitto per chi ancora non l'ha preso, abbiamo lasciato su questo tavolo il quaderno di Webvalley, ci abbiamo lavorato tutti un pochino, racconta un po' quello che è successo in questi 23 anni, speriamo di farne ancora, e quindi insomma se potete prendetevi una copia, abbiamo anche l'ebook, però insomma credo che sia un bel ricordo per tutti voi. Ultimo commento, mi piace sempre ricordare quando lo vedo, abbiamo nel pubblico anche Cesare Furlanello che è il fondatore di questa scuola, quindi mi piace sempre vederti qui e grazie che sei venuto. Grazie a tutti.
Welcome everybody to this final event of the 24th edition of Webvalley. And there's not much to add to what Claudia has already said. And if I really need to stress just one point, is that again, this team of students has been challenged by a very tough thing to do, and again, is not something that we have planned exactly for the school, but it's a part of a real great scientific project, and that's something that we are always proud to underline in this occasion. Okay, this is a very first encounter of people with data science, with real research, and what they have done and then what they are going to present you is really interesting, and I think that they should be satisfied with what they have done, and you will be too, I hope. Thank you very much, and I'll leave the stage to the kids.
Welcome everyone. I'm here to talk and to introduce you to the final presentation of Webvalley 2024. So, we are in 2018, and by the collaboration between the Italian Space Agency and the Chinese Space Agency, the first satellite of the CSES mission was launched. Its purpose was to look for hidden things between the Earth's ionosphere and electric field. More directly, its purpose was the one to see if actually earthquakes were predictable thanks to these particles. Okay, so it's a real physics laboratory floating 500 kilometers above our heads. In it, we can find many different sensors. Each one detects different things, such as high-energy particles, like protons and neutrons, plasma, or electric field. All of these to study phenomena that happens on Earth and on space, such as solar flares and gamma ray bursts. We are actually proud to say that we, as Webvalley 2024, decided to work exactly on this, going above and beyond, embedding ourselves in a real scientific research. But who are we? Well, to tackle this challenge, FBK rounded up 20 young teenagers from all around the world, everyone with a different story, different backgrounds, and different expertise. Of course, we were not alone. A big team of scientists and researchers helped us throughout the whole project. But let's talk about our goal. Our goal will be the one to study, monitoring, investigating, trying to see if there is for real a relationship between particles and waves detected by the satellite and phenomena happening on Earth and on space. But, of course, to do this, we just had 3 weeks. But how did we do this?
So to answer this question, we decided to break down our work into 3 main subtasks that we call challenges. Having this modus operandi allowed us to approach our mission from many different points of view, allowing us to tackle extensively every core aspect of this year's project. Specifically, our 3 challenges consist of catalog data ingestion, CSES data exploration, and anomaly detection. But now, let's actually delve into the tangible results that these 3 challenges were able to achieve during the last 3 weeks. The first challenge we want to introduce you is catalog data ingestion. And as we previously mentioned, our main goal is the one to study the behavior of Earth's ionosphere and the behavior of the events that happen around us, on our planet, and even in the universe. We want to study them, analyze them, and see if there's a relation that can combine these 2 types of events. But now, I feel like asking you one thing. Where do we start? How do we even do this? What are the tools that can help us to achieve this, if there's any? We asked this simple question: what is the state of the art of this field? Recognizing that today there is a strong need for a platform that gathers together all these different data, we were able to identify a gap that had to be addressed. And here is where our team finally steps in, because we built a central hub that aggregates together all these data in a comprehensive database. From this database, we then developed a dashboard that the scientific community can access in order to navigate through this data more efficiently.
So, first of all, we need to ask ourselves, what kind of data are we collecting? So, we can categorize all the data we have been collecting in three main classes: cosmic, space, and geophysical. So, cosmic events originate from outside the Earth's atmosphere, or even beyond our solar system. Space events occur within the space surrounding the Earth. And geophysical events originate from within the Earth itself. Now, between the cosmic events, we have decided to collect data for gamma ray bursts. For the space events, we decided to collect space weather events and magnetic disturbances. And for the geophysical events, we have collected terrestrial gamma ray flashes and earthquakes. So let's talk about gamma ray bursts. So a gamma ray burst is a highly intense burst of gamma rays. And a gamma ray is the most energetic form of electromagnetic radiation. So since this is a cosmic event, they are observed in distant galaxies. And you can think of them as one of the most powerful events in our universe. And this is because gamma ray bursts occur during catastrophic events, like the explosion of a star. And the picture on the left represents, artistically, a gamma ray burst that was detected from one of NASA's space telescopes. And it is believed to be one of the most powerful we've ever detected. This plot, well, first of all, this plot is the map of our universe. And the horizontal yellow line in the center is our galactic plane, which is where we can find our galaxy. And all the dots you can see are all the detections of gamma ray bursts from 3 satellites in the past 2 years. This plot was generated taking all the data we found from these 3 satellites. And we can see that most of the detections are in the poles. And so this is just to say that our galaxy is not really affected by this phenomenon. And now, terrestrial gamma ray flashes. So they are kind of similar to gamma ray bursts, but they are way less powerful, and also they happen within the Earth's atmosphere. So they were first discovered in 1994, and what happens is that it is believed to happen above thunderstorms. And that plot on the left represents, again, all the terrestrial gamma ray flashes we detected with a satellite, and most of them are in the equator, and this is probably because most of the thunderstorms happen around that region.
Space weather events driven by solar activity impact space and the Earth environments. Significant events include solar flares and coronal mass injection, release a large amount of energy that charge the particles. When these particles interact with the Earth's magnetosphere, they can cause geomagnetic storms and auroras, as we can see in the right picture. And the picture shows the northern lights, but there is also the southern lights. Then the magnetic disturbances. As we can see in the picture, we can see the region surrounding our planets and confined inside the Earth magnetic field. So magnetosphere is the interaction between solar wind and the magnetic field. Magnetic disturbances, often caused by solar activities like solar flare and coronal mass injection, are disruptures in the Earth magnetic field. These disturbances, known as geomagnetic storm, but also space weather events, can impact satellites and the GPS system also, power grid and communication network, and also making monitoring essential. Then we have the earthquakes. Earthquakes is a sudden shaking of the ground caused by the movement of the tectonic plates behind the Earth's surface. The movement results from the release of accumulated stress along a fault and a fracture on the Earth crust, as we can see in this line in the Earth. And this fracture in the Earth crust leading the release of energy in form of seismic waves. As we can see, there is the P waves and the S waves. And studying earthquakes in general, along with also the space events, is crucial because it helps researchers explore potential connection between the magnetosphere and the lithosphere.
And in fact, what information are we actually retrieving about these events? Well, here's only a few examples of the types of data that we gathered for each event detected by satellites, sensors, and gathered in our central hub, showcasing, for example, the trigger time, or when the sensor was first triggered by the event, or the gamma ray burst as an example, the flux of the space weather, which is basically the rate flow of a physical quantity according to the event, and also the magnitude of earthquakes, in which we tell us the intensity of the earthquake according to the Richter scale measurement. But these are only a few examples of all the data we gathered. However, the real question is, why is it important to consider all of this data together? Well, it's because researchers study the data from the ionosphere and physical events to find relations between them. And so, we propose a solution to easily access this information with precision and efficiency, contributing to the scientific community and thus being a relevant instrument for scientific research.
So, we've explained to you what was the purpose of our challenge. Now, I'm trying to explain how we did actually our project. This question that you see on the slide was the key question we had to find an answer to, and it represents the main challenge of our project. We had to find a way to build a tool that was capable to gather a great quantity of data coming from different sources. This was the main difficulty of our challenge. In fact, as you can see, we didn't download all of our data from a single source, but we actually used more than one. They were all public sources, but they were very different one from each other. Here we have some examples. We downloaded some data from NASA, for example, for gamma ray bursts, TGF, and magnetic disturbances, from USGS for earthquakes, Space Weather Live for space weather events, and others, such as SSDC or ISDC. The problem was that all these sources were actually very different. They displayed the data in different ways, and so we had to find an efficient way to put them together. And how did we do this? Well, we decided to divide our working schedule in 3 different phases. The first phase was the web scraping one. Web scraping is a technique that can be used to download data from a website. In this case, as I was mentioning before, it was quite difficult because we had a lot of sources and they were very different one from each other. So, even after downloading all the data, we were in a bit of, let's say, a chaotic situation. For this reason, the second phase, that is data harmonizing, was necessary for us. Data harmonizing is the process of unifying, putting together disparate data fields, finding similarities between them, and maybe bringing them to a unique format. Data harmonizing was probably the most challenging part of our project, mostly because of the great quantity of data we had to deal with. To give you some numbers, after web scraping, we had more than 70,000 events to deal with. So you can understand that data harmonization was not so easy for us. And finally, after the harmonization, we have the last part of our project that consists of the creation of a database. Finally, a ordered database that makes it easy to access all our data that we have been downloading. In this slide, we would like to give you an example about the importance of data harmonization for our challenge. Here, you can see 4 different fields that are called T90, T50, start time observations, and end time observations that we found when we downloaded all the data. At the first sight, you might think that since these fields all have different names, they might represent different type of attributes, of characteristics of the data. In reality, all these fields refer to a same concept, that is the time interval in which the phenomenon that we were studying happened. However, you can understand that to build an efficient database, we couldn't use 4 different fields to refer to the same concept. So, obviously, data harmonization was very important for us, it was necessary for us in this case. Now, let me tell you something about the technical tools that we actually used to make our challenge. Well, for the first part, so sources, web scraping, in general, the downloading of the data, we use Beautiful Soup and Selenium, that are 2 Python libraries specifically for web scraping. Then, we built a database, an SQLite database. One of the main features of this database is that it is dynamic. And it must be a dynamic database because all the events that we are studying, terrestrial gamma ray flashes, gamma ray bursts, earthquakes, continue to happen every day. And of course, our database must be up to date with new data and must include even the most recent data. And we managed to do this implementing cron jobs in our database. So now the database each day updates itself. Each day, in particular, we perform a new web scraping of our sources, and we upload the new data, if there is any, into the database. And finally, for what concerns the final part, the web app, what the user sees, we use both Django, that is a powerful Python web framework for the backend part, whereas we built up the front-end part using JS, HTML, and CSS. Also to make an interface that should be good looking and should be attractive for every user that wants to use it or simply wants to try out our website.
And with all of these technical tools presented, we were finally able to assemble this big web application, which is a user-personalized tool that gathers multiple cosmic, space, and geophysical data from many public datasets and provides them in a single source. And in order to consolidate our SPADE website, we also had to consider our visual choices, which are the name, logo, and also the overall layout. Initially, the name SPADE is composed by 2 words, the word space and detection. That together, they also form the word spades, which is actually our main logo, which also resembles the symbol of a rocket. And regarding the layout, we were able to design a more and mainly friendly interface system. And combining all these elements, we were able to create our interface look that initially looks like this. So at the bottom of the interface, we have the main table of information, showing all types of data in a clear way. Above it, we have all the tabs about types of events from which we gathered information, from earthquakes to magnetic disturbances, as an example. And in the upper right corner, you can see the icon for the filters that allow more precise search for the data, and also an information icon where you can easily see the meanings of all terms and the definitions used in our website. And not only that, we have our time period table in order for the user to choose even more specifically data that they are interested in. And in the left upper corner, we have a graph icon where we show our data in a visual way. However, these are only a few examples of the features in this PAY website, which we will show in more depth now with our demonstration.
So now it's time for the demo. This is our web app, the main part of the app. As you can see, there are 5 tables, one for each category we studied, like earthquakes and magnetic disturbances. The user has the opportunity to select what columns he wants to see and also rearrange them to make sure to understand the data better, because it's fundamental to be able to see correctly all the data. The user also can select the time period up to 10 years, because for performance reasons we can't really show a lot of data all at once. But the most common one is to use like a few months, but the user can also select manually the data they want to analyze. Next up, we have the catalog, which shows the meaning of each column, because it's very fundamental to understand the difference. And also we have a PDF file that shows a more specific meaning of each column. Next up, if the user wants, for example, to download the data to analyze, for example, using Python or other libraries, they can also download data using JSON, Excel, or CVS format. Also, the search bar is useful to search for all events that happen during a specific time frame the user chose. For example, the search for Indonesia for earthquakes that happened in the last 3 months, in this case. We also have graphs that show each level of magnitude for each day, like a median. We have GRBs, and also a full column for all events that happen during a day. For example, we can also filter them out using the top layers above. We can exclude maybe some kind of events or anything else we want or don't want to see. And that's all for the demo.
And however, we don't plan on stopping here. These are our future plans for the SPAY website. We will reach out to institutions, organizations, researchers, and websites. For example, University of Trento, the National Institute of Nuclear Physics, the National Institute of Astrophysics, in order to search for collaborations and enhance our data and make our project known. Not only that, but also we will personalize even more our user experience through the implementation of a notification system, which will notify the user about the arrival of new data in our SPADE website. And last but not least, more data scraping, in order to keep SPADE as updated and complete as possible, gathering more data in a single source to facilitate the access to this information by the scientific community. And what's more about the SPADE web application? Well, it will be useful for this scientific community because of its extensive documentation that we stated before, that assembles all the information needed to interpret the data we featured in our database, showcasing a catalog which will have all the definitions and explanations of possible unknown terms by the user, that in a clear and objective way. We also provided an API or application programming interface that allows data downloading in JSON and other formats, facilitating access to our data that can be easily integrated with other external systems, helping not only the scientific community, but also the challenge number 2, which we will present now.
So, hello again, everyone. This time, as team leader, I will be presenting you our task, which is data exploration. This one has a big goal, which can actually be summarized in study, store, and plot 12 terabytes of data coming directly from space. Of course, we don't have just that. The real aim is the one to create an easy tool available for researchers from which they can find and plot and study easily, in a matter of seconds, many different types of data from the CCES 01.
Test? Okay. So, what kind of... Okay, I'm too small. Here we go. Okay, so what kind of data are we actually looking at? As already mentioned, we are dealing with data from the CSES-1 satellite, which was launched in 2018. And it's orbiting around Earth in around 500 kilometers of altitude. And here you can see an image, an image of the satellite. And what is CSES-1 actually measuring? It has different payloads on it. Basically, a payload is just some kind of instrument that you put on a satellite, and then it's called a payload. So CSES has many different payloads to study different phenomena, and especially we are looking at high energetic particles. So this sounds fancy, but actually we're looking at protons, electrons, and photons that are around the Earth. So also we can measure electric fields. Maybe you see these kind of blue antenna that stick out of the satellite, and they are used to measure the electric field. We can also measure the magnetic field with CSES and the plasma that is around Earth. And thus, CSES orbits around Earth and gathers all this data for us. And when it has collected data, it sends the data back to Earth. So CSES orbits around Earth, passing above the North Pole and the South Pole. And when it has completed one tour from the North Pole to the South Pole, or from the South Pole to the North Pole, we call that a semi-orbit, because it has passed around Earth half a time. And for each semi-orbit, we get one file for each payload of CSES. And normally a payload contains multiple sensors, so in each of these files, there are data for different sensors. And depending on the specific sensor, we get between 1 and around 4,000 measurements per second of this payload. And one semi-orbit takes around 47 minutes. So we complete around 30 semi-orbits per day. For each of them, we get these files for every payload. And the data we get from CSES, we can't really deal with it at first because it's just a big table containing a bunch of numbers. So we get these gigantic files, and now we must do something with it, because we can't just look at the numbers and understand what's going on. So we have to somehow visualize our data in order to be able to actually extract information from it. And that's where our challenge starts.
So as Emma previously mentioned, the CSES satellite has a large variety and a large quantity of data. And because of this, it has so much potential to really help the scientific community expand. And this is our main implication and application of Challenge 2. We mainly want to contribute to scientists a way to connect all of the data associated with CSES. Because this data is really representing the geophysical, solar, and cosmic events that are occurring around the world, we want to be able to interpret this in a way that is visual and user-friendly for those that are using the tool. And in doing so, we are also able to transform the complex and large quantities of data into something that is more digestible for users. By displaying analytical results, we're able to allow scientists between all of these fields to collect all of this data and analyze and create collaboration and connection between them.
Hi, so like they said, we have 12 terabytes of data, but what is that actually? So just to visualize how much data that really is, that's roughly 600 million sheets of paper. So to visualize that data is super important, because visualizing the data to analyze it is way easier than looking through those 600 million sheets of paper. So our tool, we wanted to visualize this data, and not just visualize it so you have to dig through to find the visuals. We wanted to make it very user-friendly and easy to use. Because I'm sure you've all used web applications before where you're digging around to find what you need. We wanted something where it's right there for you, you can easily access it. And if we achieve these two goals, our third goal will be super easy. So with this easy-to-use web app, researchers can find new research studies or questions based off our data. So this is our development process. The first thing we did was research and understand the data and how to visualize it. We then broke up into small teams and started working on individual tasks. And once we completed those individual tasks, we built them all into one tool. And after we built this tool, we asked actual scientists what they thought of our tool, what needed fixed, and we made the changes that were needed. And then we restarted this process and refined our tool. So now we're going to talk about the actual tool.
So we wanted to create an easy and an effective tool. For doing this, we implemented some different type of indexes methods. Indexes helps the user to select only the information that he really wants. First, let's have, First, let's have a brief overview of the type of data we are working with. Our data are stored in a data frame that we created. The data frame has different columns. We have the file name, the payload, the geographic coordinates, the start date, and the end date of the semi-orbit, and obviously the orbit number. The primary purpose of indexing is to extract relevant subsets of data that meet specific criteria, making our analysis more efficient and focused on the material that we want. Indexing is crucial for several reasons, like efficiently, relatable, the scalability, and for extracting only the real material. Okay. Now we will take a look on a filter that we have when we start our demo. This is a screenshot of the demo. The user can select from this part the type of geographic coordinates that he wants to see the data from. He can decide to zoom in the map or zoom out, and with different types of polygon, he can decide the coordinates. The user can even decide when he wants to start the documentation, so he can find the start date and the end date. Here we can see another filter that takes out the payload of the information that he wants to see.
After filtering through the data, we actually need to plot it. But how do we plot the data that we want to filter through? We used the Plotly Python library to plot our graphs so that our graphs are interactive, which allows us to hover over and get information about the specific points and zoom in and zoom out to better understand the data that we want to analyze. We also implemented into our tool many types of statistics, such as means, standard deviation, minimum, and maximum. The main way we plotted our tools is with time series. A time series is a plot in which on the x-axis there is the time, and on the y-axis there is the actual intensity of the measurement we want to take. In this case, speed, and the plot shows the geomagnetic storm of during a specific time period. But sometimes time series aren't enough to plot the data. What do you think we can do in that case? Of course, we plot more time series. One on top of each other more time series one on top of each other are called aggregated plots, and one next to another are called sequential plots. The aggregated plots are used to better understand the patterns between the data, the various types of data we want to analyze, and the sequential plots are used to get a better overview of the things we want to analyze. In this case, we can see an aggregated plot with the latitude of the satellite in a specific time and the electron density of that the satellite measures on the y-axis. In some cases, however, we want to represent three-dimensional data arrays. In this case, a two-dimensional plot would not be sufficient. So we need to use, we use energy tables or spectrograms. In this case, we can see an energy table. On the y-axis, we have the energy. On the z-axis, we have the hue as a logarithmic proton density, and on the x-axis, we have the time. Energy tables and spectrograms are useful to understand the patterns and find some specific, we can call them anomalies. The final method with which we plot our graphs is geospatial plots. Sometimes a time series is not enough to represent the data we want to analyze. These two graphs are represent the same thing, but in the first one, it is easier to understand what the graph actually means. On the z-axis, we can see the count of electrons during the orbit, which we can better understand that on the time series in the beginning and in the end, nearby the poles, there are more. However, in the geospatial plots, we can see that in a specific zone, which is this one, there are more electrons. This zone is called the South Atlantic Anomaly, and it is a zone in which the amount of electrons is higher.
After completing the initial phases that included the analysis and full comprehension of both the structure and content of the data, we needed to transform and merge our work from individual modules, such as interactive plots, statistical figures, and geographical filters for the data, into a practical, useful, user-friendly tool. To achieve this goal, we relied on many different libraries, such as Pandas, GeoPandas, but mainly on Streamlit. Streamlit is a powerful Python library that enables us to develop our own web tool called Spectra. As we always said in this journey, there is always room for improvement. We already tried, but as a next step, we are looking forward to fully integrating, whenever there are unexpected behaviors in the graphs, the possibility to confront easily with complete catalogs coming from the database of Challenge 1. We integrated complete and different components into Spectra, which was quite a challenging task. This tool aimed to simplify the work of researchers, saving them a lot of time and efforts on a task that is usually very difficult and time-consuming. During the upcoming demonstration, you will see our Spectra in action.
So, upon entering the Spectra web app, we can first enter the Filter tab, where we can select our first of two filters. The first filter being the geographic region filter, which allows us to zoom in on any area on Earth and select a particular location. So in this case, we're selecting the country of Italy, and this is the region which we will filter through to look for files within this region. And now we're selecting the start date So we're selecting the 1st of February of 2022, and we're going to select a range of 20 days in the month of February. So this is the range of time which we're looking for. And then we're searching for files within this region and within this range of time. And as you can see, these are the files we have. And then we are able to select the one of 7 payloads we're looking for. So we're selecting the LAP sensor to plot. And we can select a ascending or descending orbit and the sensor type. So on each payload, there's various sensors, and in this case, we're going to be plotting the A311 and the A321 sensor, which represent the electron density and electron temperature, respectively. So this gives us an overall plot of the statistics for all of these files displayed above. And as you can see, we can plot the 25th percentile mean or median and the 75th percentile, which gives us a general representation of how the data looks like. And as you can see, these graphs are actually dynamic. So we can zoom in on specific areas, hover over points to see what these specific data points look like. And then we can actually plot over this graph with a specific orbit number, which allows us to visualize the pattern of one specific file. So we're entering one specific orbit number, and as you can see here, this line, the blue line plotted over the statistics, represents that specific file. And the electron density is a little bit above the general trend of the rest of the files. And after we plot this, we can move on to the single semi-orbit tab, which allows us to plot one single semi-orbit, one of 7 payloads, or multiple if we choose to. So in this case, we're going to be plotting the EFD and the LAP sensor for the same semi-orbit number. And we have to filter through, again, all of the files based on the criteria we select. So again, we're selecting the LAP sensor and the EFD sensor to plot. And with the EFD sensor, we're able to visualize the 3-dimensional data, as Marco mentioned previously, with energy tables, as you can see here. And this is a time series for the same data represented above. And then we are able to plot a geospatial map with the map behind it. And as you can see, the S shape is actually the path taken by the satellite when it travels around the Earth. And the concentration of yellow particles near the bottom half of the image represents a greater electron density, as shown by the scale of colors on the right. And then after this, we can move on to the multiple semi-orbits tab, which allows us to plot multiple files at once. So instead of selecting one single file, we can select multiple files for a single payload and plot all of the files either sequentially or aggregated. Sequentially meaning every single file is one after another, and aggregated being one on top of another. So we're selecting the EFD sensor and the HEPH sensor. So this is an aggregated plot where the lines are one on top of another for each line representing a different file. And we're confident that our tool will provide a new method for interacting with the CSES data for researchers, and we're confident that it will open up new opportunities for research, specifically in the field of anomaly detection and recognizing patterns within this data that previously couldn't have been extracted before. And speaking on the topic of anomaly detection, we'll now hand it over to Group 3.
Challenge 3 is about anomaly detection. More precisely, in Challenge 3, we focus on developing a model able to detect anomalies. In Challenge 3, we aim to spot anomalies collected from different payloads of the CSES-01 satellite. And since you may be wondering, why do we want to do this? Well, we want to find relation between anomalies that we find in the satellite data and events that happen in Earth or in space, such as seismic events or space weather phenomena. Well, in order to do this, we need to tell anomalies and nominal data apart. But how? Well, we developed a deep learning model. And just saying this is oversimplifying the labor that we put into the work and all the commitment that we had. So, to truly understand what we did, we need to divide our challenge into 3 main parts. One being data selection, second one being preprocessing the selected data, and third, training and testing the model on the preprocessed data. But before going deeper into these 3 main points, we need to understand first what kind of data we are dealing with. So to understand that, I will leave the word to Gil, who will guide you through understanding it.
So this is our input data. We have data from 4 payloads, 6 instruments. The first payload is a high-energy particle package, and specifically in it we have low-energy sensors, high-energy sensors, and X-ray sensors. We also have a GPD, high-energy particle detector. We have an electric field detector, and we have a Langmuir probe, which measures the temperature of the electrons. This graph shows the amount of data points that we have per payload in a logarithmic scale. And our data, just like it as group 2, is time series data. And as Marco explained, time series data is just where the time is a specific axis. So just a couple of measures with intervals between them. So for this example, we have the proton counts from the HPPL instrument averaged on 1 day. And before doing pre-processing, we have to select the data that we work with out of the 12 terabytes that we had. So first of all, we decided to remove day orbits and focus only on night orbits. This is because solar energy from the sun may disturb the model. And the second thing is we decided to remove data from the South Atlantic anomaly. This is because the Earth's geomagnetic layer is much weaker near the South Atlantic, and it can also disturb and make spikes in the data. So now to the pre-processing phase.
Okay, so basically now we have filtered data and selected data for training the model. But is it sufficient to actually train the model this type of data? Probably not. You may be wondering why, and why is this part maybe one of the most time-consuming and effort-consuming ones in our challenge? But, well, you can kind of see it in this data. This was an example of HPPX X-ray rate raw data that we had, and you can see count of photons in the y-axis and the the time in the x-axis. You can clearly see that there is something that doesn't really is okay here. So you can see that this is a really big peak because this is a logarithmic scale, and if it was a linear scale, you couldn't even see the graph, because it's so big in respect to the other part of the graph. This is completely normal because these are precise sensors which have not 100% accuracy and have errors. So this is normal, but we can't feed the model this data. We have to filter it and to pre-process it. So in this case, you can also see these types of peaks, which we can't take as important features. The important thing that you have to understand about this is that we have to, before making the model understand our data, we have to understand it first. We have to actually understand what our data means, and then, only then, we can feed it to the model and try to understand what was the outcome of the model, because we already know what we wanted to extrapolate from our data. So we have to highlight the important aspects of our data. And here, you can see an example of pre-processed data. This is the same exact example as before. This is the same data, the same semi-orbit. And you can see that the starting peak was removed. We just removed the first timestamps of every type of this feature data. And we also sampled the data in n seconds timestamps. So for example, here we divided the data by 10. For each second, we did samples of 10, and we did the median between those timestamps. So with this procedure, we both compress the data and make it lighter, and also remove the peak that we didn't want, because the median removes outliers. So this is an example of normalized data, but this is just the first step of pre-processing. So maybe now it's more clear why actually when you work on data science, before actually going to the model, you have to have clear data which highlights the important aspects of your data, not the ones that maybe are there just because of maybe sensor errors or other biases that you can't take as good training data.
So after pre-processing, we have to remove all the trends from each block of data, like sections of the map. We separated it by sections because the satellite travels around the Earth. It goes to a bunch of different regions. So each region has its own trend. We can't just subtract like one big line. So what we decided to do is we decided to separate we decided to separate the map into different blocks, Each block has its own data set. We can see it here, where this green data goes into this block, and we did that for all of our data, as you can see. So after we did this for each block of data, we detrended each block of data. We did that first by making a fitting function for each block. After we make the fitting function, we need to get the fitting result from that function and subtract it from the data. When we subtract it from the data, we get our residuals, which is our detrended data that we can use for training and testing.
So now we get to the model part, the real part of this challenge. We decided to use deep learning, which is a class of models, a recent class of algorithms, which can fit function to data. We chose a subclass of these algorithms, which are called multi-head transformer. They are the backbone of algorithms like, and bots like ChatGPT, because they have what is called an attention mechanism. So the data in them can be cross-correlated. So the input, as you can see by this phrase, the input data can be cross-correlated with each other so that the model can interpret each point with its own importance. So that could be useful for our task of anomaly detection. So, and we took our model from this paper, which is Anomaly Transformer, and we adapted it to our model. So what the model is based on for anomaly, real anomaly detection is a reconstruction error. So our model is given as an input a time series, a window size, and it spits out a reconstructed model. And then when we have these two sections, the input and the output, we can check them and see if they match. If they match, that means that the model has reconstructed the data and it's a normal part of data. It's nominal data. But if it isn't, then it could be an anomaly, so that has to be checked. To do that, for this type of payload, for example, this is an HAPPL payload part, and you can see there is a big spike in the middle. That is an anomaly that we want to check. So this is what we are searching for with our model. But how do we actually do this? So first of all, as we clean the data, which was a huge actual part of our task. And after cleaning the data, we separated it in two. We had about 2 years of data and 400,000 data points. So we chose a point about in the middle to divide our training and testing dataset. The training dataset is the one which we will use to train the model, and the model will see and fit to it. The testing dataset, the model will never see it before the testing phase, so we can check if the model has generalized well by checking the part which it has not yet seen.
So now, after all of these different steps, we were finally ready to start actually training the model. As Alessandro just said, we divided our dataset into two parts, and the first part is the one that is used as input in the training process. What the model does is, as it gets fed the data, it becomes able to recognize the trends and the patterns and use them to reproduce in a better way the input. And as close as the reconstructions gets to the input, the better it works. We defined a way to see how the progress of the model of the training is going. This is the loss function. The loss function is defined as the delta between the input and the reconstruction. And as the training goes on, we want this delta to get as small as possible. Here is a graph that shows the loss score as the epochs go on, and we can in fact see that the loss score decreases, which means that our model is learning. Our model is progressively able to reconstruct better what we give in input. After the training comes the testing part. The testing part is absolutely crucial because it's a way to see that the model is not able to reconstruct effectively only the data that it has already seen, but that the model is able to work on new sets. Here we have some plots. in which we can see proton and electron counts from the HPPL payload. Highlighted, we have a time frame in which the model detected lots of anomalies, which are the red lines. This means that the model is telling us that in that period there was some activity which was strange. And to check that this is an actual anomaly connected to real-world events, we checked some catalogs. And in fact, we can see that in this exact time frame, there was an important solar flare. This is dated at the 2nd of November 2021, and this solar flare lasted a few days. We can see two images. The first one is a picture of the sun in the visible spectrum, and the other one is a plasma density chart. These two graphs show us that the model was able to recognize anomalies in new data that it had never seen before. So this means that our model is in fact able to correctly recognize and detect anomalies in space weather events.
So now that we know that the model can work, we have to train more models. We made actually 8 with different payloads. So we checked both with single payload experiments, and then we did some multi-payload experiments. So we can check how each payload can help us to get the data we need. And actually, it helped a lot. It took quite a while to train all these models, but at the end, we had 8 experiments, which we fused together and put a threshold on them. So we said that 5 sigma, which is 1 event in 2 million, is the minimum threshold for an anomaly, and everything above that is going to be an anomaly. And then we plotted it. So this is the final result. As we can see, we have all the 8 models, and in every event that more than 6 models detected an anomaly on, we can easily correlate them with a space weather event. So this means that the model is correctly seeing in the data, in all this data, in this enormous amount of data, which parts are actually anomalous and which parts can correlate to space weather events or in events in general.
And so now that we're approaching the end of this presentation and the end of Webvalley, what are some of the real implications of what we've done in the past 3 weeks? To sum it all up, for the first week, we learned about the scientific basis of the project that we worked on. And then for the next 2 weeks, we teamed up and worked on the project in separate teams to team up and separate all the work. But what have we learned with all of the work that we've done? On the technical side, we spent a lot of time learning and getting familiarized with the astrogeophysical observations and all the scientific basis that we had. This helped us not only understand this project, but also gain an appreciation for the real implications of what we've been doing. On the other hand, we've used data analysis and different approaches such as machine learning to really tackle the challenge in depth. But more importantly, we learned of the power of collaboration. Within all of our teams, since we all come from different backgrounds and have different skill sets, we were able to not only learn from each other, but put all of this together and tackle the challenge together. And on the other hand, we also learned of the importance of design thinking. Since many of us had to find products and a way to further the scientific field, we also had to think about what the scientists need and what is currently lacking in these fields. And finally, since all of these challenges had different aspects to work on, we also collaborated with each other. We shared different methods and different functions, as well as advice to each other, helping us achieve a common goal. So what have we achieved in the past 3 weeks? Looking at the current collaboration in the scientific community, our contribution to community was to innovate on what is currently there. We looked at different tools to connect the solar, geophysical, and cosmic fields, and then we presented results in different ways to encourage scientific collaboration, while also taking new approaches such as machine learning and deep learning. We can see that in between all of these challenges, there is also a lot of collaboration. Spade making all of the catalogs and allowing all of the data to be viewed together. also encourage Spectra to be able to visualize all of this data. And the anomaly detection model created by Challenge 3 was able to analyze all this data in a different way. And we hope that because of all of this, we are able to create a research ecosystem. And since there is not a lot of collaboration between these cosmic, solar, and geophysical fields currently, we hope that this ecosystem will allow scientists to work together and find correlations between all of these fields in the future.
So what is the actual infrastructure and the hardware that we actually used to make this project? Well, it's important when you have such a big project made in team like this to make everyone work with the same environments and the same machines, because you can't make everyone work with its own environment and try them to merge the work, because it will probably not be a good idea. In our case, we worked with cloud Linux virtual machines provided by Azure, by Microsoft, and we were able to actually have a scalable environment and an environment which was equal for everyone. So we were able to actually measure work pretty easily, and we already know what we had to do to set up the environment. What is the good aspect of this? It's the fact that you have the same environment in all machines. So for example, in this case, when we needed to actually upgrade the computation power, because we needed to, we updated to Airflow, which was a really good machine that was provided to us in our laboratory, and we SSH'd in, and were able to actually do all the heavy computation that we needed. So we were able both processing the data and training models and plotting graphs. We were able to do everything, and the good thing about this is that we didn't need to reset environments or everything, because it was the same Linux environment, and we just changed machine. So that's the definition of scalable. Now that we talk about what we actually did in these weeks and the project in these 3 weeks, let's talk about the future. How is this project going to be useful to people from tomorrow on, now that we finished our work in Webvalley? Well, we have 2 big goals that are in the long-term future. And the first one is data source integration. With this term, we mean creating a unified dataset which anyone can use in the research environment to actually merge all the catalog data relevant to the CSCS mission. So they can take the data from the satellite and try to check that it matches with our unified dataset. So they can have a whole dataset that they can actually use without being mega computer scientists, because retrieving that type of data is not so easy. And cross-validating with the CSCS data maybe is not for a physicist in most of the cases. So we want to make data accessible to every researcher to actually expand the research in this field. That's the long-term goal. And the second one, which is probably most ambitious, is an early warning system. The idea behind this is to make our model better and better to actually detect in real time the anomalies that occur in space weather and seismic events. So the idea behind this is to actually have a system which is able to take the data from the CSCS and match it with catalogs in the training to actually understand what is happening in real time and send warnings to the scientific community. That's the idea. Obviously, this is kind of hard to realize, but a good point that we have in our future and in which we trust a lot for the future of this project is the fact that it's all open. The whole project is open source. You can check it on GitHub, and you can even collaborate to it if you want. And that's a really good point about this, because research, when someone does good research, always new research born from it. So people can actually create research from research that was already made. And that's the whole point about open source. It's not only about having a software which is free. It's moreover having something in which you can collaborate in and in which everyone can put their effort to make a better final product. So, for example, CSCS-01 is just the first satellite of its kind, and CSCS-02 is probably going to be operative in a few months. So the really good thing about this is that we already have a tool which works, and the perspective is to make it work always better, to even work on new satellites. And that's the perspective that we have with the open source mentality, because you can actually make everyone collaborate. So now we will just thank everyone who made this project possible, because obviously we worked a lot, but without the collaboration of tutors and all the organizers, this wouldn't be possible. They worked even a lot more than us. So we will start to thank, obviously, Fondazione Bruno Kessler for organizing all of this, especially Giuseppe Jurman and Claudia Dolci for actually directing this and organizing it all. Then, in a technical aspect, we would like to thank the University of Trento and the INFN and the Italian Specialty to actually give us lectures and make us understand what is the real challenge. And obviously, the Limadu project, which is connected to the CSCS-01 satellite. We would also like to thank the Artigianelli Institute for accommodating us in their labs, and the Arcivescovile for accommodating us in their dorms. So we could actually have a place to sleep. Special thanks to the Provincia Autonoma di Trento and to ISEF for making this project international and making people from all over the world collaborate to it. So thank you for your attention. I hope you liked the presentation. And now, if you have any questions, feel free to ask them.
Thank you very much. I invite you guys here on the side, maybe divided in two groups, and I invite you as a scientific committee here just to try to guide a bit this question and answering time. Thank you very much for being here with us.
Okay, well, good afternoon. My name is Leonardo Ricci. I'm a physicist. And, actually, I'm rather unprepared to say something because it's really amazing what I've just saw, okay? So congratulations, really, because it's really incredible what we have achieved in just I would say a couple of weeks, and it's really amazing, really. And well, I have a question, a more philosophical one, in the sense that you have, as I know, you are students of high school, coming from all over the world. And my first question, you actually addressed a problem of physics, of modern physics, of a real one, because I'm working with people that actually are handling this data every day and are very good physicists. And so I know that this is a very tough problem. But my question is, what is the role of math in all you have done? Because you have gathered data, you have organized data with wonderful tools. I suspect you used Python to manipulate all this data. But now my question is, what is the importance of knowing mathematics in real math, calculus, geometry, arithmetics? What is the role of math in your work?
Wants to answer these questions? Maybe raise a hand so you will help me in choosing one of you. Thank you, Lavinia.
So, okay. Does it work? Okay, so I think that the role of maths is fundamental, of course, because we're speaking about physics. But when it comes to handling data, maybe one of the problems that our challenge faced less, but the other ones faced more, is even understanding what some kind of data means when it comes to different ways to even plot it, or like reference systems. There was a lot of work behind in the first week, especially in lectures, understanding what unit of measurement, and especially how can you pass from one another. And even when it comes to all of the theoretical stuff about physics and magnetic field, clearly there were some parts of physics and math that we were missing in the explanation. Like in school we haven't done even integrals yet because we're just in the 4th grade of high school. So we had to really focus and maybe add some parts of math knowledge that we didn't have yet, which is really important when it comes to everything concerning physics. I think that they're very deeply interconnected.
Thank you.
Thank you very much.
So, thank you. I'm Francesco Nozzoli. I'm a researcher in the INF and TIFTA. And then I was surprised that your slides are much more beautiful than mine. But I have a question. You work on this anomaly detection. Did you find something anomalous in the data? This is something that is curious that you cannot explain. This is maybe the most important and beautiful part of our job, to find something that is surprising you.
Alex?
So the anomaly detection connections, we didn't really do a lot of them. So we did the model and the catalog, we saw a lot of anomalies that the detection told us, but we couldn't really explain a lot of them. Like, we saw them, but we couldn't explain. A little bit for time, but this is really an open project. So we did the baseline, we cleaned the data, we started making models, but now the job of the scientists who will come after us will be exactly this, like seeing what our model has said and see if it makes sense at first, and then if it can't be connected with anything else. Because, yeah, we saw them and we detected them, but we still yet don't know what they are. So that's to see if the model is wrong, something that we don't know is there. So we'll have to see.
Thank you. Thank you.
Okay, so I'm Francesco Di Miccoli. Also, I'm a researcher at University of Trento and also in TIFPA. And first of all, I would like to join my colleagues' compliments about the huge amount of work that you were able to accomplish in just a few weeks. And I would like also to say that as physicists, we are always craving for tools like these that can gather information from a wide array of sources together to check if there are some correlation in the measurements. So this is really our job, and tools like that are fundamental for us. So thank you. I was very curious looking at the last part of the presentation, about the training part of the model. So as far as I understood, correct me if I'm wrong, you have a model that tries to subtract from your data the steady part to check for anomalies, to spot anomalies. But since the steady is not really steady but is constantly moving, you need some kind of intelligence that tells you this is steady and this is anomalous. Okay. So I was very curious to check what is the rationale between in the feeding the algorithm with training samples. So you just feed with every data and let the algorithm understand what is steady and what is anomalous, or you do some kind of preselection of time period, for example, in which you don't observe any visible anomalies, and you tell to the program, yes, that is really steady, so learn that this is steady. And last question, which is your level of confidence about the result? So can I really trust the fact that I have 5,000 anomalies in that particular month? Or maybe there is some kind of estimation of an error on this number? Thank you.
So the training, how we did the training was completely unsupervised. Okay. So we did not give any labels to the data, and the data was fed into the model as it was and used also as training. On the training set, we did not remove any of the known anomalies, but that's because we had the prior to say the anomalies are so little that the model can still generalize well enough to spot anomalous data. So we actually, what we showed was were the anomalies in the test data, but also in the training data, the model doesn't say, oh, there's nothing because I was trained to say there's nothing here. But it found also some anomalies in the test data.
Okay.
So that's how we fed it. We fed our time window. We told the model, please reconstruct this. Like the model first took it, put it in a latent space, so like encoded it in its language, and then tried to reproduce it as it understood it. So if it was normal data, then it would be able to reproduce it easily because it has learned the patterns, how nominal data looks. But if there was an anomaly, then it would not be able to reconstruct it as well. So if there's a spike, for example, we can see that that spike is not as the model intended that part to be.
Okay.
So this is a subsection of models which is autoencoders, which it's not actually an autoencoder, but it works on the same paradigm with this reconstruction error. That's the loss function that we use. That's the score that the model gives us. Yeah. For every point, we calculate how different it is from the real data. Yeah, okay. So that's what anomaly means to us.
Okay.
Oh, and the confidence, I forgot one question. So the confidence of the results are really a hyperparameter. Like the model gives us something, and then we have to decide how we are gonna see that output of the model. Because like the model gives us a score. What he thinks, how different he thinks that data should be, actually. So we must set a threshold. Like as we've seen, we set a 5 sigma threshold, but like, we didn't really have time to tune that in because like in a real world application, you would have 3 training sets. A training set, a validation set, and then a test set. That validation test is used to tweak the hyperparameters, which are the threshold and things like that. So it's not really like, we're confident, but it's not like how we would have done it if we had more time. Like that's the point.
Okay. I think that you surely didn't have enough time to do a proper performance study, but a typical procedure that one can do is, for example, inject some anomalies that are controlled by the user. Like, for example, you have steady data, you inject some peak that you create, and you check if the model is able to spot it. I don't know, maybe you did something similar, or
you create a peak if you know that a peak is what anomaly you want to see. But we didn't actually see what our anomaly looked like at the start. So it was completely unsupervised, because if we knew what we were looking for, then we could have gone on a semi-supervised route or even supervised. But we didn't know, because the task was find anomalies in this data. We don't know if there are, we don't know which are, but there are. We know that there are anomalies.
Okay, thank you.
When you say find, you say find. You are talking to the machine, right?
Could you elaborate?
No, because my feeling is that I'm an old guy, you know, and so I'm still confident that artificial intelligence is just something artificial. And so, no, I'm trying to explain. When you say that your system is unsupervised, okay, you're saying that, okay, you have this time series and then you tell your system to produce some score, and then in order to say whether you have an anomaly or not, you just set a threshold on the score, and if the score overcomes the threshold, then there is an anomaly, right?
Yes.
Okay. Have you tried, have you tried to use just noise? So to produce a noisy time series, and that's just say, and then see.
Well, that's certainly one of the tests that we would have done if we had more time. Certainly, I can say we started training the models like yesterday.
No, it's fine.
Yeah, no, we started 2 weeks ago actually. But those would be things that you would do if you were training models. But the things that we had, we didn't even know what to look at.
Okay.
Like the model part was what we can't arrive at. Maybe a function approximator can look at it in another way that we wouldn't look at it.
Okay.
That's the point.
Okay. Again, on this topic, you mentioned, or someone mentioned, 5 sigma confidence. Who said that?
I did.
Ah, you did. You are the culprit. And so, could you please elaborate on that?
So, there's been quite a wrangle on all this stuff. The 5 sigma was on the threshold. We put like 0.99993 of the data we looked at. We say that is not anomalous.
What does it mean of the data? 0.9993 of what?
We see all the scores. We get all the scores from the model. We say, okay, the model has said 0 3,000 times, 1 1,000 times, and then we take that and we set a threshold on that.
Okay, understood. Volevi fare un'altra domanda?
Sto pensando.
Ok, no, possiamo anche finire.
Just a curiosity as a future user of this stuff. It's killing me, sorry. Okay. I'll kill her. Okay. You mentioned that you were able, maybe I dreamt about it, but is it able to do correlation between any variable measured? So you can do a bidimensional plot of, for example, electron versus proton counts, for example, in a certain period of time. Is it?
You're talking about the visualization tools.
Yes.
Who wants it?
The human part of the.
Can you reform the sentence?
Oh, sure. You can show time series, so any variable against time as a function of time, but also any variable against any variable. So I mean, for example, can I produce a plot of, I don't know, electron counts as a function of in Y and as a function of, for example, electromagnetic intensity in X? So
no, for now not.
Okay.
It's everything on time series or scatter plot, and one of the features is like you can for example print overlaying one function on top of the averages, but there's only it's on the x-axis is always latitude or UTC time, or for example when you do aggregated, you put not UTC time, you put the start of the measurement and the end of the measurement, so you can do aggregated plots. If you want to do sequential, you use UTC time, or if you want to do aggregated, you can use also latitude, or it's always on the function, on the axis is always time or latitude.
Yeah, that's already impressive. I saw latitude on the x-axis, so I figured out, okay, every variable can be used as x, but I guess that in the future it will be possible. Thank you.
So guys, how many of you have decided or are thinking to do the physics then after this experience?
You can raise the hand or
It was a terrible one.
yes. It was a horrible experience.
How many computer science? How many maths? One. And how many will just, what do you say? They just will leave STEM forever? Okay, none as well. Okay. That's really I can say, a lot of hope in people like you, let me say.
Any questions or comments from this side of the room? Okay, David? So, Professor Rosinger is the professor. He is coming from South Florida University, and he stays with us these last days of Webvalley as observer. So thank you very much. Please.
No, thank you. When Nicholas Barbe introduced me to Claudia last year, Claudia said, you need to come to Italy and see the students in action. So it was an easy decision for me to spend my university's euro to come to Italy. But she was right. Watching these students, the work that they were doing, graduate level work, this was a doctoral dissertation. And to do it in another country's language, for most of you, speaks to your intelligence, your enthusiasm, your passion, and your dedication for what it is you want to do. The world needs more folks like you. I want to thank you for welcoming myself and my colleague Justice to observe what it was that you're doing. I want to thank Claudia. You're treating us like family. We've only been here for a couple of days. The tutors who answered our questions, the students who put up with us when we were asking you questions and you're probably trying to code and be like, no, I want to code, I'm in the zone. Let me code. Don't ask me about this. But we need more students like you. We need more programs like this. Because this is our world. This is where we're going. And the ability to come here and think about all of the possibilities to be able to expand in some capacity, to bring this incredible program over to the United States is an exciting opportunity that we're very proud to be hopefully part of and have discussions when we get back. So if any of you are thinking of University of South Florida and want to come to America and study there, come talk to me. But once again, thank you for the hospitality. I cannot wait to see what you students do in the next years to come. The future is in good hands. Thank you.
Thank you, David. I think your words are perfect to close this edition of Webvalley. So my emotion already, I think, rised, I don't know, the roof. So thank you, guys and girls. It was really a pleasure to having with us this edition. Now I think it's time to celebrate these 3 weeks. The prison is finished. And congratulations, really, from all of us.